or predicted a CMB, I think. And he also told us everything we know today about large-scale structure in the universe. And in particular, he told us about cold dark matter. And today he's going to tell us whether Lambda CDM is alive or sick or... Please.
Thank you, Avishai. It's nice to hear those words from an old friend. Here are my topics. I'm going to spend most of the time on two. The major developments, you could call them the paradigm shifts. I call them here transformative ideas that led us to where we are now in cosmology, with an attempt to draw some lessons from what happened in these transformations. But I think it's well to start by having a look at the universe in its present state, for which we're trying to find a theory. So here is a nearby galaxy, much like our own, a flattened disk, rotationally supported, rotating at roughly constant linear velocity, the angular velocity then decreasing going outward, so there is shear. You see the dark lanes where interstellar dust has settled and is absorbing starlight. You see blue regions where stars are forming. The more massive of the stars, very hot, very high surface temperature, blue light. It's hard to see the stars themselves because they tend to be buried in dust clouds, but you can see light glinting off them. Here and there you see red patches where massive stars are emitting enough ionizing radiation to produce a plasma around them. And the recombination in the plasma has the prominent H-alpha line in the red, giving this glowing red here and there. You see a glow of yellow light toward the center. Not so clear in this image, but the yellow light spreads all over this image. The light of some 1,000 million stars, roughly like the sun. In our neighborhood of our galaxy, there are at least as many planets orbiting stars as there are stars. It's a good bet that in this galaxy there are some 1,000 million planets on which all sorts of fascinating things are happening that we, the human race, will never see. There are many other galaxies. Here are a few more nearby ones. M101, I just showed you. Here is the nearby galaxies have known distances, so we can make a three-dimensional plot. Here is the plot in orthogonal projections. You see the distinctly clumpy distribution of galaxies. The brighter ones are marked in red, and examples down here. There are many more less massive galaxies, I suppose, with many more planets doing interesting things. The clumpy distribution, you notice, is very apparent. On a larger scale, you see this distribution of the brighter galaxies. This selected by brightness on the sky, and that selects for the most luminous galaxies, ones like the ones you've just seen. This is a section of the sky about that big across, containing several 100,000 galaxies, counted by hand in the 50s by Donald Shane at Lick Observatory. Divided into pixels, and where the pixel is bright, there are several galaxies, or 4 or 5. Where they're dark, there are none. Here you see a strong clump of galaxies, the Coma cluster. It has the shape of a galaxy. It is a galaxy of galaxies. You see a mess all over, but you notice something new, that this side doesn't look very much different from that side. On a still larger scale, one sees this map. This is a map of intense radio sources. This is a rare phenomenon where the center of a galaxy explodes for reasons that are not well understood. The explosion is visible in the radio for an enormous distance. Here, some 10,000 radio sources plotted. You're looking out near to the Hubble length, where the recession velocity approaches the velocity of light. You must be careful, of course, that this is not observed. The instrument can't reach that part of the sky. Here is the brightest radio source in our galaxy. It confuses the antenna around it, so you don't see anything. You can see perhaps an arc of sources rising like so, although I can't see it from this direction. Sources in the Milky Way, our galaxy. And why can't I? Yeah, here. That aside, this has all of the clumpiness of what you saw on the last map, but sparsely sampled and sampled many times over as you're looking in clump after clump in projection. The result, the homogeneous universe. This is central. I count this as a transformative idea because it means, under the assumption that the universe is a stationary isotropic random process with a coherence length that's small enough that we can get a fair sample, that we are allowed to think of a theory of the universe rather than specific parts. That I count as a really deep advance. We can think of a theory of the universe. This great idea was introduced in its modern context by Einstein, 1917, when people were still wondering what galaxies are, although they did know that the spiral nebulae are distributed in a very irregular way across the sky. And it becomes the interesting question, what was Einstein thinking? As best I can deduce, it is based on this comment in the wonderful book, The Science of Mechanics by Ernst Mach. Mach, you know, liked the idea that motion has meaning as relative, and that inertia also only has meaning as relative. He remarks on an experiment that Newton conducted. I stand on a platform that is free to rotate about a vertical axis. I hold a bucket of water. The water has settled down to steady state. I look at it. If the water surface is curved, then I know when I look up the distant stars are moving. If the water surface is flat, the stars are stationary. Surely, Newton argued, this means that rotation is an absolute concept. Mach said nonsense. No one is competent to say how the experiment would turn out if the sides of the vessel were many leagues in size. A marvelous anticipation of lens-tearing drag. Einstein loved that notion, but the best indication I can see of why he felt he had to introduce a homogeneous universe is from lectures a few years after the founding paper, 1921. It was known then that general relativity theory would allow a solution in which there's one galaxy in asymptotically flat space-time. That galaxy may rotate with all of the usual effects of rotation, and yet it is rotation relative to empty space-time, quite non-Machian. Einstein's solution introduced, as a boundary condition, you might say, the condition that there is no asymptotically empty space-time, there's matter everywhere, homogeneity. This is the quote from his book, as you can read, his lecture. A very influential argument. People jumped on the notion that the universe likely is homogeneous well before there was any evidence of it. But he was right. A big question remaining, still somewhat debated, perhaps should be more debated. Was Einstein right for the right reason? There's a related issue, I think. You're all aware of the anthropic argument. We had to live in a galaxy because we had to have had a few generations of stars burn, produce heavy elements. The heavy elements trapped in the potential well burned into another generation of stars that made more supernovae, then allowed the formation of some of this nuclear waste in the form of a planet, Earth, around a star that could be then left pretty much alone for some 10 to the 9th, 10 to the 10th years. The big question that haunts me a bit, why so many galaxies? We needed a galaxy. Did we really need 10 to the 9th L-star galaxies? Does inflation require that we have 10 to the 9th galaxies visible? I give you two hypothetical situations. First, we have a larger lambda, so that only 4 sigma fluctuations can make galaxies. Then we would be sitting here in a little island, maybe 1 or 2 galaxies, empty until a long way off another little island. Could have happened. Is that more probable?
Depends how you define probability.
Oh, good. We will go no further. I believe that in inflation our universe is not boundless, that there is an edge. The edge could have been seen, could it not? We don't see the edge. Is that suspicious? Let's go on. The expansion of the universe, I remind you of a simple symmetry argument. Here, can anyone see that? Ah, look at the screen, you see a triangle. You notice that I have drawn the triangle at two different epochs of the universe, one larger than the other. But the triangles are self-similar. Is that the word? Similarity. The lengths of each length scales in proportion to its length. Here it is. The lengths scale in proportion to a universal expansion factor. That means the logarithmic derivative of the length is the logarithmic derivative of this cosmic expansion parameter. This, of course, Hubble's law. Now, of course, these lengths are measured on surfaces of constant time. We observe along the back light cone, but if the distances are small, the difference is small, and so you require a linear relation between redshift velocity and distance. Discovered, I think, as far as I know, first by Georges Lemaitre in advance of the observational evidence in 1927, then experimentally discovered independently by Edwin Hubble in the US. I pause to remind you that I'll be talking about redshift factors. Divide the observed wavelength of light from a distant object by the laboratory wavelength and call that 1 plus the redshift z. So, let's look at the evidence that Hubble found. This is his 1929 discovery plot, perhaps not overwhelmingly impressive. But impressive to me deeply is that by 1936, he and Humason had gone to a redshift 10% of the velocity of light. Really impressive. Impressive when you also consider that getting the next factor of 10 took more than 70 years. We make progress in erratic ways. Here is the linear redshift distance relation. Here is a bit of curvature, of course, of great moment, as we'll discuss. But let us first pause to notice something I think is of great educational value, edifying. If the universe is expanding, as suggested by the redshift, is the universe evolving? As I'm sure you're all aware, at least in general terms, there was the possibility discussed in the 1940s that continual creation is keeping the universe in a steady state, expanding, the old galaxies drifting away out of sight so we're not overloaded with them. New galaxies form through the continual creation of matter. The important point for this comment is that the universe has to have this line element. Can't have space curvature, because if there were space curvature, it would be evolving, and this universe is not allowed to evolve. The Hubble constant can't evolve, so a dot over a is going to be equal to h, a constant, so it has to be an exponential expansion. You might recognize this as a pretty good model for our universe as it is, and a pretty good model for these measurements, which here show the deviation from, I think this is Einstein de Sitter. Interesting to consider that if we had this redshift magnitude relation, and we didn't have any other good cosmological tests, then we would have a strong faction who would say, well, look, steady state has predicted this curve. And would we not, therefore, have an established cosmology, the steady state cosmology? It requires a means of spontaneous creation of matter. It might be a difficult thing, but you know, young people are very clever. And I'm wondering if, under these conditions, we might not have ended up with a version of inflation, the steady state theory with continual creation of matter rather than galaxies. I make this point and I emphasize it because it's so easy for us to be led astray. The steady state cosmology is really pretty elegant. It requires a few minimal assumptions, makes then definite predictions. And one of the predictions is verified. Why are you resisting this? We are very fortunate, therefore, that we have a lot of tests of our standard model. It's easy to be led astray, but much more difficult if you have lots of independent tests, to which I now move. The first of these, of course, is the microwave background radiation. Here I remind you of the general game. We have an occupation number for thermal radiation. This occupation number has to be conserved by Liouville's theorem. Remember that the momentum of a photon is a canonical variable, canonically conjugate to its position. Liouville tells us that the occupation number is independent of time along the path of the photons. In a homogeneous universe, this means that n has to be constant everywhere. As the universe expands, the frequency decreases as the wavelength increases. And so the temperature has to decrease. And since the temperature has to decrease by the same factor at each frequency, it means that if you start with thermal radiation, you'll stay thermal. And that's all I have to say about that. I have a historical interlude. I couldn't resist pointing out the first recognized detection of the microwave background radiation, this thermal radiation from the early universe. Here you see an early experiment in communications at microwave wavelengths. This was giving us all those wretched cell phones that our students wandering our halls of our university and perhaps yours always seem to be consulting. It started here. In this experiment, you know, I think I got two slides mixed up. I wanted to show you. Yes, this was the experiment. You notice the rough Planck's, a rough-looking antenna, but actually a very sophisticated one, a horn reflector antenna. In the 60s, you used to see these all over the US, probably here too. They're excellent for microwave communication because the radiation comes into this horn and comes along like so, and it is very efficient at rejecting thermal radiation from the ground. Inside that little shack was some very sophisticated traveling wave maser amplifier down over here. Here you see numbers for the accounting of sources of noise, the maser being very well calibrated and understood. And here you see backside or back lobe pickup 2 degrees, which was a fudge. The engineers couldn't understand whether they were getting too much radiation, so they ascribed it to the antenna, even though they knew darn well it couldn't be the antenna. But what could it be? We've seen that. Arnold Penzias and Bob Wilson, a bigger version of the horn reflector antenna, the deep puzzle, they went to extreme lengths to demonstrate that this system was receiving more radiation than it ought. It was news of this experiment, David Wilkinson, Peter Rowland behind, a Dickey radiometer, smaller, but it doesn't matter for diffuse radiation. Looking for the radiation, Penzias and Wilson realizing that they had the radiation, and great excitement. Here was the Penzias and Wilson data point, 7 centimeters wavelength. Princeton coming in several months later on a black body curve. Getting that black body curve was a real heroic effort and culminated in 2 experiments. Here's one group. Dave Wilkinson is here and a host of others. A NASA COBE satellite, a Nobel Prize for John Mather, who's as tall as I am. Not so well advertised that in Canada, a rocket experiment took the same amount of time to build, roughly a decade and a half, led by Herb Gush, a picture that inspires confidence. I say that because here is one of my favorite pictures of scientists at work. Whenever I see this, I smile and ask myself, if I didn't know these guys had done something great, if all I had to judge by were those images, would they inspire confidence? Which, of course, is the lesson there. You shouldn't ask such questions. Instead, you should look at what they did, which is truly magnificent. Here is COBE, 5S experiment. Solid line, a Planck curve. Here's the Canadian Gush, Halpern, Wishno measurement. Either one settles it. Wow. Here is the modern collection. Single frequency experiments, this solid line from phi-RAS, not a theory, that's a measurement, with error small compared to the size of the line in a Fourier transform spectrometer. Just a gorgeous fit to a black body spectrum, a thermal spectrum. You can't see the thermal spectrum, but it's in there. It's here, yes. This, to me, is a deeply transformative development. Thermal radiation in the universe, which is optically thin, how could it happen? Surely it means that the universe evolved from a very different state and that we're seeing fossil evidence of that early state. As concrete to me as dinosaur footprints and bones and eggs are, that those improbable creatures once walked the earth.
Jim, can I ask a question?
Of course, please.
This Harper was 1990, the mother also was 1990.
Yes, they were
It was the same or
within months.
within months?
Within
And
months.
error was
Oh, much tighter here. This is 10 minutes rocket. This is years. Of course, this was not years. This was weeks. But Jacobi operated for years and beat these error flags down very, very small. But for a demonstration of a thermal spectrum, there it is. There is one technical point. One should, to be careful, speak of a thermal spectrum, not a Planck blackbody spectrum, because what is required is that the occupation number be some function of this h nu over kt. If that is the case, then all of the experiments done, precision experiments done in measuring the spectrum and measuring the dipole and higher multiple anisotropy will work as if it were a Planck spectrum. You play the same game. The occupation number is what counts, and it is conserved. So that whenever you have a Doppler shift in the frequency, you'll have a shift in the temperature. It will be the same at all frequencies, and so a thermal spectrum will remain thermal. That's important because the spectrum measurement you saw was not an absolute measurement. It was rather a comparison to sources that are measured to be very black and have well-calibrated temperatures, and you're matching that source to the radiation background. So what you have shown, what they have shown, is that the spectrum is very close to thermal. I am told that the last check that a thermal spectrum is Planck is 1929. Here it is. It looks pretty good, but people nowadays know how to do an awful lot better. Here, an interesting philosophical question. Should experimentalists be given the funds to check that a Planck spectrum is a thermal spectrum? Should this be tightened? No one in this room, I wager, has any idea that there could be any difference between a thermal spectrum and a Planck spectrum. Should you therefore spend the money to check? I'll leave that for a vote. But my vote is, you got to do it. Friedman-Lemaitre cosmological model, let's pause a moment and notice the curious twists and turns of the parameters in this equation. Homogeneity and isotropy requires the Robertson-Walker form. General relativity requires a form of this sort, mass density, space curvature, readily parameterized as a density parameter in radiation, in matter, space curvature, and cosmological constant, where these parameters add up to 1. And then through the 80s and the 90s, heated debate on what are sensible values for these parameters. Inflation was deeply influential in the early 1980s. Space curvature is ugly. Away with this term. Vacuum quantum energy density. Ridiculous values. In fact, you recall that as the universe expands and cools, it goes through phase transitions in which latent heat is released, and gives us an effective cosmological constant that changes by an enormous value at each phase transition. We end up where? Well, if lambda is interesting for cosmology, we end up with a cosmological constant expressed as the fourth power of an energy of around 1 milli-electron volts. No self-respecting particle physicist cares about milli-electron volts. It's got to be 0. Everyone knew that in the 80s and the 90s. And of course, let's face it, Einstein de Sitter, with no space curvature, no lambda, is the elegant case. It must be what the universe is like. Well, as we know now, space curvature is indeed tiny, if it's there at all, but we must learn to live with lambda. I used to enjoy giving colloquia, learning to live with lambda. But while I pause for a moment, you recall this early meeting of Einstein and Georges Lemaitre, the Belgian, who discovered Hubble's law. I wonder if you can see, this is signed Albert Einstein. This is signed Millikan. It's hard to make out. And he has such a black robe that in the original you can't see whether he signed it. Einstein at this meeting, it might have been this meeting, young man, your mathematics is all right, but your physics is dreadful. Away with an expanding universe. Later, correspondence, a letter to Einstein from Lemaitre, arguing, Albert, you ought to give some thought to lambda. And thank you very much for your kind letter. Since I have introduced this term, I have had always bad conscience. This is referring to lambda. But at that time, I could see no other possibility. I cannot help to feel it strongly, and I am unable to believe that such an ugly thing should be realized in nature. So here we have the authority. A transformative development in the, was this the 80s? Yes. Redshift samples had gotten large enough that one could start to measure relative velocities of galaxies. A simple game. We're instructed that redshift is proportional to the distance, but there are peculiar velocities. Two galaxies that are close to each other will pull on each other and cause motions. One can estimate those motions statistically by looking at a two-point correlation function in which the transverse distance is as observed across the sky. The radial distance is the redshift. If there were no peculiar velocities, the two-point correlation function would be isotropic. It's not isotropic. You see an elongation along the line of sight. That elongation is due to the relative motions of galaxies. From the amount of elongation, you can get the relative amount of relative velocity. From velocities, it's pretty easy to estimate masses. And you get masses that are convincingly below Einstein de Sitter. This is the present situation. Of course, the data marvelously improved. And you can see the growth of clustering on larger scales by the compaction on larger scales. That's the flow of galaxies together as clustering grows. But this is good enough. It was obvious in the early 80s that we had a choice of ugly decisions. The popular one was that the universe is Einstein de Sitter, but the galaxies are much more strongly clustered than the matter. It was very popular and it had to be considered, but it never made any sense for a simple enough reason that if you only allow galaxies to form in high-density regions, then why do the galaxies in low-density regions look so normal? Another alternative considered, space curvature, ugly. Lambda, ugly. Falsification of lambda, maybe general relativity doesn't work. But we had the Lambda CDM Cosmology. I just remind you that it assumes general relativity theory, spatially homogeneous and isotropic random process. The initial conditions, very carefully described, initially adiabatic, Gaussian, growing, scale invariant. That was one choice. There were many others, but it's simple. Flat space sections, textbook matter and fields, and hypothetical non-baryonic dark matter. Later, we had to add lambda, and we had to add tilt from scale invariance, and we have to add neutrinos, lots of details. key point, I wrote this down only to show that the clumpy distribution of matter is not inconsistent with the smooth distribution of radiation. You can see how the dark matter, cold dark matter, helped on that end. It doesn't disturb the radiation when it moves about, whereas plasma moving disturbs the radiation. There are lots in the 1990s of other ideas: hot dark matter, cosmic strings, explosions. My favorite, exploding superconducting cosmic strings. Lots of ideas out there. Lambda CDM was established by detection of fossil from the Big Bang, the acoustic oscillations. Early universe, matter is hot, thermally ionized. Thomson scattering causes matter and causes baryonic matter and radiation to behave as a fluid with viscosity. In the early universe, a given Fourier mode has an amplitude that will grow, gravitational instability. In time, though, the wave can see that it is a wave, and it will start to oscillate. Here is the nearly coupled radiation in red and baryons in black oscillating until we get to a time when the universe is cooled up to a point that the hydrogen that the plasma can combine to hydrogen, release the CMB, and release the baryons. Meanwhile, the cold dark matter grows with everything else at high redshift. It doesn't see any pressure, so it stays smooth, more or less, and gives us a density fluctuation. Here, an old image just showing that the result of this is a power spectrum that has big oscillations. The oscillations are too big because we didn't have dark matter yet, but it gives you the point. The power spectrum is oscillations. You recall that the autocorrelation function is the Fourier transform of the power spectrum. That means there's a bump in the power spectrum. Fourier transform of a sine wave is a delta function. So I show here the Planck satellite image. It's gorgeous, and I think this is real, not computer-aided design. On the outskirts, Dickey radiometers. It pleases me to compare this to the Dickey radiometer invention paper, where you see things like output meter, and you see here 1800 RPM motor. Things have gone a long way, but of course the basic technology is there. And out of Planck has come the power spectrum of the radiation distribution across the sky. You recall that this is the analog of a Fourier power spectrum. Expand the temperature across the sky in spherical harmonics, square the amplitude, average over the different m values for given L, because they're all the same angular resolution, multiply by L to protect the innocent, and you get such a curve. The oscillations, the residual oscillations in the radiation distribution due to the growth or cancellation of the waves as they reach decoupling and are released. The fit is magnificent. The parameters tuned to exquisite accuracy. And now we have to get to pause and ask ourselves a question that I'm motivated by the question about the steady-state cosmology. If this were the only cosmological test we had, would it convince you that the Lambda CDM model is a good approximation? You bear in mind that it has 6 parameters, and perhaps you have heard John von Neumann's statement: with 4 parameters I can fit an elephant, and with 5 parameters I can make its tail wag. Given the brilliant ability of bright young people to invent things, what are the odds that this could be a fluke, a good fit to the wrong theory? We are very fortunate that we don't have to make that judgment because we have other tests. You know, I haven't been keeping track of time. Have you?
22 minutes left.
Total. Good. We noticed that those waves left in the radiation should also be left in the distribution of baryons. And indeed, they are here seen. This is the space Fourier transform power spectrum, the square of the amplitude of the Fourier transforms, showing barely detected but clearly detected wiggles. Here the general trend taken out, and you see the wiggles quite well. Here again, a two-point correlation function in redshift space. What I showed earlier, buried way in here. This is a much larger scale. On intermediate scales, you see a squishing. That's the motion of galaxies together. On average, galaxies are moving together because the clustering of galaxies is growing due to the gravitational instability of the universe. And then out here, you see a faint trace. That is the Fourier transform of the oscillating power spectrum of the matter distribution left at decoupling. The Fourier transform of an oscillating function is a delta function. Of course, it's not quite a delta function, but there it is detected. I think on polite company, we needn't bother about all of this. You have two effects to worry about. You have an angular size distance that tells you how to translate this angle into a length out there. The length, you notice, is determined by what happened up to decoupling. That depends on the density of baryons, the density of dark matter, relative to the density of radiation. But it can't care about lambda, and it doesn't care about the present value of Hubble's constant. Once you know the present temperature and the baryon density and the dark matter density, you know what happened at high redshift in this theory. You can predict this radius. And having done that, I got it confused. There it is. You can predict the radius of that sphere where the 2.4 correlation function peaks up at different samplings of galaxies. Here they are, a low redshift sample of galaxies. Compute the Fourier transform, find that bump. Here, intermediate redshift. Here, high redshift. The solid curve, the Planck 6-parameter theory fitted to the Planck measurements. And an absolutely dazzling effect. And this can go on for some distance. You remember that in the old days, people focused on the redshift magnitude relation. And here Alan Sandage, with the theoretical cosmologist and theoretical chemist Richard Tolman, a design for the great 200-inch telescope on Mount Palomar. This was in the 1930s. The design changed, but you can see there they were hungering to get at this redshift magnitude relation. Here the paper in 1961, the 200-inch telescope at last in operation. The paper, the ability of the 200-inch telescope to discriminate between world models. Steady state here is here at -1. And that's pretty close to our universe and other parameter combinations. And as we've discussed, this transformative development, which gives in this paper omega matter 0.31, no, here it is, 0.3, Planck 0.316 plus or minus 0.14, a much more precise measurement. But really the point here is not precision but accuracy. We're all familiar with the difference between precision and accuracy, right? No. Any experimentalists say, well, of course. Precision refers to the number of significant figures you can establish reproducibly. Accuracy is what remains after you take account of all of the systematic errors. These measurements are so wildly different from the measurements of the acoustic oscillations that you can be very sure the systematic errors are going to be different too. Difficult measurement, but convincing enough to show you that it agrees with the Lambda CDM model fitted to the WMAP and other anisotropy measurements. I can go on it this way. My computer is getting... just one more example. Distant quasars provide nice beams along the sky that may encounter intergalactic or may encounter clouds of baryons. In those clouds of baryons, there's lots of atomic hydrogen. The atomic hydrogen has a strong resonance line, the Lyman alpha line. This is the bottom of a Lyman alpha absorption line seen in this quasar. There's also another resonance line from Lyman beta, from n equals 1 to n equals 3. And Lyman delta, n equals 1 to n equals 4, and on and on and on and on and on, up the chain of n's. You see absorption from the ground level to each of these levels. You see the trough of, it's broad because there's a high optical depth in this line, but you see another line on the side, that's deuterium. And by combining all of these lines, each of which gives you a probe of the amount of hydrogen and the amount of deuterium, you get a nice ratio of the amount of deuterium relative to hydrogen. In a hot Big Bang, there is production of heavy elements in the early universe. I remind you that to begin with, at temperatures greater than an MeV, any complex nucleus is thermally dissociated. You have only neutrons and protons and pi naughts and electrons and positrons and neutrinos and antineutrinos. When the temperature drops to about 10 to the 9th degrees, electrons can be combined with neutrons to give protons. Protons can combine with neutrons to give deuterium. And once deuterium is formed, it can burn to heavier elements. The amount of burning of the deuterium to heavy elements depends on the baryon density. The higher the baryon density when the temperature is 10 to the 9th, the more thoroughly the deuterium is burned away. Knowing, therefore, the amount of deuterium, you have a measure of the mass density in baryons. Here it is recorded that this measurement requires a baryon density given by this number. The 6-parameter fit to the CMB measurements, Planck and earlier, gives this number. Again, a wildly different means of testing the theory, yet consistent results. So the point has been made. I think, oh, I should mention one thing. You will still hear on occasion the statement, look, you are attempting to make an empirical theory of the universe by using what you can see. You can look back in time along the light cone. It has a thickness of what, a century? That spectacularly thin light cone is what you can see out in space. You can also look at remnants of what's in our neighborhood. For example, you can look at stellar evolution ages and infer something about what happened along this line. You can look along this line as in the redshift magnitude relation. But that's it. But that's not right. It's important to notice. For consider that here, where is it, is a galaxy seen at redshift 3. You see absorption lines in it that give you, this is another D to H measurement, a deuterium measurement. You are measuring the amount of deuterium that accumulated down here. You are comparing it with the radiation that originated way over here. You are comparing in two different regions and getting consistency. You look at the distribution of galaxies at more modest redshifts. You see these acoustic oscillations, which you're again comparing to what happened over here in the radiation. It is pretty densely sampled. Oh, and here it is. Lots of measurements. So I think it is clear that it has passed a deeply demanding set of tests, this theory. There are, of course, equally obvious, this is not the final empirically based cosmology. Slava has been working on this very deep problem, advances being made. Also notoriously open. What is this hypothetical cold dark matter? Is it really as simple as a free gas of particles? Kind of insulting to think that that big sector of our universe, containing most of the mass these days, is so simple. Whereas if you could look from the dark sector into our sector, well, depending on how closely you could look, it's a little hard to imagine the dark sector seeing our sector, but our sector is a lot more interesting than that. Surely there's more to it. An emotional argument, but let's follow it a little. And here is something I'm going to talk about a great deal tomorrow. maybe the properties of galaxies is something to teach us about the dark matter section. I draw your attention again to this galaxy, and including this section, which is vastly enlarged by the Hubble Space Telescope, to show you that there is a tiny star cluster, relatively tiny. It's about 1 million solar masses. Around it, you see dust lanes. There are dust lanes running all the way in, almost to the dead center. Dust settles onto the plane. It doesn't float much above the plane or below. It's dissipative. If it's absorbing starlight in here, then that must be because the stars are in the plane. It seems that this galaxy is almost entirely supported by rotation all the way to the center. It's a striking point, don't you agree? Here's another galaxy. Whoops. It's called Sculptor. Seen edge on. Ask yourself what you see as you run your eye across this. You don't see any feature at the center. It looks like it's a plane all the way in. A plane. That's really surprising within Lambda CDM, I argue. Well, nearby there are lots of... this galaxy has a bulge of old stars. Bulges of old stars in spirals appear very commonly in simulations. This is a good galaxy. This guy is an oddball. This guy is an oddball, according to the astronomers. It's an oddball because it has something like an elliptical up here that someday will do damage, I guess. But in this poor image, you can't tell. This is another Puritas galaxy, another. They're common nearby. This is really puzzling, and I here illustrate why. How many minutes do I have now? 10? 10 minutes? 5, 10. Okay, so here's the simulation. It's a couple of years old and so dreadfully out of date, I'm sure. I made the first substantial Nbody simulation in about 1969 while visiting the Los Alamos National Laboratory, where, you know, atomic bombs are designed. I was an alien, a Canadian, so I wasn't allowed in the inner gate, but I was allowed in the outer gate where there were computers, weapons grade, in which I was allowed to do numerical simulations. I did an Nbody simulation. I reached, I think the record was 300 particles. I had a little pathetic bundle of IBM punch cards. And because this is a serious security problem, I had to be accompanied by somebody, which degenerated into a secretary sitting reading a novel while I put my pathetic little pile of punch cards and did integrations that lasted all weekend. This has, what, 10 to the 12th particles? Something just intolerable. In this simulation, we have done the following thing. Here is the present universe, 3 different simulations. Don't plot any particle that's outside the nominal virial radius. Plot particles that are within 3 kpc of the center. That's about half our distance from the center of our galaxy in yellow. Plot those between 3 and 7 in black. Keep the label on previous plots at earlier times. So a yellow particle is plotted yellow everywhere. A black particle at 3 to 7 kpc plotted black. And anybody's out here is never plotted. So what do you see? At redshift 3, the stuff that was at 3 kpc or less now is here spread over, what is the scale? 300 kpc. Given h, it's about 400 kpc. This is spread out all over the place. Here at redshift 1, still spread out quite a bit in all cases. Here, just to remind you that the star formation rate per unit mass was much bigger in the past, roughly better than an order of magnitude between redshifts 1 and 4. That's when most of the stars were made, if we understand the star mass function well. Lots of stars made. Where are they? Where would those stars be made? I would have guessed they're made in these yellow patches and the black patches. Reasonable. Where are they now? Well, where am I? Yeah, I wanted to get here. A star that's made while things are still contracting together is not going to end up in a disk. It'll go flying through the disk and form a bulge or a stellar halo. It's a deep puzzle, I submit, that we have these many pure disk galaxies in which the stars had to have formed in the disk after dissipative settling of gas. You can't make them out of pre-existing stars. So how the devil did these guys get formed in abundance? One thought I hear is that this is an exceptional region. Well, in fact, it is very difficult to repeat this sort of sampling at much greater distance. Hard to know. So, I think I've come to an end. And I've decided to end with some reflections on what I see learned in this story of how we arrived at the hot Big Bang Lambda CDM cosmology. First point, natural sciences is social construction. You may know that those are awkward words in many circles because some have taken it to mean that since societies can operate in very different ways, why couldn't societies invent many different natural sciences? And what particular reason do you think that our natural science is better than anyone else's? That, of course, is absurd, as we'll discuss. But I think it does have a very particular significance, namely that just as science operates in fits and starts, we must expect that science operates in fits and starts that are to be distinguished from brilliant ideas, magnificent collections of observational evidence. The whole point is that the fits and starts tend to be dissipated as people start looking at evidence, and that the interaction of theory and observation has tended to yield theories that are so thoroughly cross-checked as to convince us that they're very likely a good approximation to reality. It's important to say that we haven't demonstrated unambiguously mathematically that any theory is right. In fact, no theory is right. They're all incomplete. I don't know an exception to that. All of our scientific theories are incomplete. But we have ideas on how to improve them. We are working on that. And we're making a big assumption, either that we are converging in these successive approximations by ever better theories to the final theory, or else that it's successive approximations all the way down. But I'll stop there.